All right, hello everybody. So this sort of module that we're working through here, right, module 6, is basically like weird trees. So first we looked at binary heaps, which are like trees that get packed into an array. And now we're looking at a thing called a disjoint set, which is going to be a weird tree where you can go up but not down. But first, let's talk about like what are we sort of trying to accomplish here, right? So a disjoint set is a data structure for tracking collections of sort of like equivalent objects. So we have a bunch of objects, and then some of them are equivalent to each other, and some of them are not here. So we're going to sort of define equivalence according to this definition here, right? So number one is every object is equivalent to itself. Like if you sort of ask, hey, is A the same as A? Then the answer is yes, always, no matter what, right? This property here is called a reflexivity, if you've kind of heard of that before. If I could spell it correctly like that, right? Just every object is equivalent to itself. Our next requirement is if an object A is equivalent to some other object B, then the other way is true also, right? Then B is equivalent back to A there like that, right? This property is called symmetry. And if you want to put a name on it there like that. And then finally, if we have three objects and A is equivalent to B and B is equivalent to C, then I can kind of like shortcut that and be like, okay, A is equivalent to C. And this property here is called associativity. Associativity. If you have sort of these three things here, right, then you have what in math is called an equivalence relation, but that just means it works like equality, right? It works the way that like things being equal sort of works there like that. It also works for like all sorts of other things here, right? So like the example I gave here is right is if you sort of say that like being neighbors, if you sort of allow yourself to be your own neighbor, then that fits this definition, right? Then if I'm your neighbor, you're my neighbor. If I'm a neighbor to like you and you're a neighbor to somebody else, then like we're sort of I'm neighbors to the third person there like that. If you have like objects or something and they're like sort of touching each other, then that would kind of work according to this definition. Every object is touching itself. If I'm touching you, then you're touching me, and so forth there. So like lots of things kind of fit into this sort of mold of things here. Disjoint sets are like for me they're kind of like a frustrating data structure because I always find myself working on problems where I need them, but they're not in the standard library of basically any programming language that I know. Like they're not in the C++ standard library. You can't hashtag include disjoint set. They're not in the like the Python library. They're like no programming language that I know of has disjoint sets as a sort of built-in thing here. So I'm constantly being like, oh, this is a problem for disjoint sets. Guess I gotta build my own again here. So if you sort of take that definition of equivalence that we had up there, you can kind of see that we can like group them. Like we can take all the objects that are equivalent to each other and put them into like some sort of like group where it's like, oh, these are all the things that are equivalent. And then over here I have another group of these are things are all equivalent there like that. And if you sort of follow from the definition, right, we know that every object is going to belong to at least one set, at least one group, because every object is equivalent to itself. So even if there's nobody else that is equivalent to me, I'm in a group by myself. And then finally, no object will be in more than one group, right? If I'm in a group with object B and I'm also in a group with object C, then associativity kicks in and says, well, we're all in the same group there. There's no way that like one object can be shared between two different groups here like that. So you can think of a disjoint set as like a data structure for tracking sort of like this idea of groups, of like which group does an object belong to when an object can only belong to one group at a time. So like here's an example, like this is completely hypothetical, right? Definitely not like a real thing that I've done here. Imagine I have a bunch of movie files on my computer here, right? They're, I got them all, they're all legally, they're just home movies, whatever, right? There's so many files here that I have some duplicates. Like the file names are maybe different, but the movie content is the same there like that. And of course, movie files are big files, right? So comparing them is expensive, right? Like comparing one file that is 6 gigabytes in size to another file that is 6 gigabytes in size, that like sort of takes a while here. And of course, like these days, storage is getting expensive. Like a a 2 terabyte SSD costs about $1 million or something. I'm saying this in 2026. So I want to be like efficient, and I want to go through my movie files and identify the duplicates so I can just keep one of each sort of collection of duplicates here. If I have n many files and I just am like, okay, I'm going to compare this file to every other file, right? I'm going to have to do n times n minus 1, which is n squared minus n comparisons. And that'll take me a while. Since my movie files are big, this is going to be kind of slow here. So the idea is, if I am able to sort of leverage about what I know about equivalence here, maybe I can cut down on the number of comparisons. If I have some movie file that is named A and I discover that it is equivalent to another movie B, and then I discover that B is equivalent to C, I don't need to compare A to C. So I can skip some of these comparisons, and maybe I can cut this down from n squared to something more sort of manageable there like that. So a disjoint set is sort of like a thing for tracking as we discover that things are equivalent, what the sort of group structure of the whole setup looks like. So let's say that I have 7 files here to keep things sort of manageable, right? And we'll label our files as just F0 through F6 here. So I want to group all the identical files together. And there might be, there might be sort of like more than one sort of file per group here like that right there, right? So initially, I just assume that there's no duplicates. I assume that every movie I have is like a unique gem of cinema, right? So I put each file in a group by itself here. Now let's say that I compare file 0 and file 1, and I discover, hey, wait a minute, these are the same movie. So I put them into a single group here. So I'm merging the group containing F0 with the group containing F1. I sort of smoosh those two groups together there like that. So now they're in the same group. Okay, I continue sort of like, doing this here, right? But once I have more than one thing in a group here, we're going to pick what's called a representative here. In fact, like I would have done this like earlier here, we always sort of have a representative. So a representative is just one of the things in the group, and we're like, that identifies this group here. So like I'm drawing a star above the representative for the group here. So if you're like, hey, F1, who's your representative? It's like, oh, my rep is F0. If you ask F0, hey, who's your representative? It's like, I am my own representative there. So each group has a unique representative, and that's how we identify a group, is by its representative. This just frees us from having to worry about 2 different kinds of things here. So I don't have files and groups of files. I just have files, right? Like if I want to know like what group you're in, I just ask, what is the file that is representative of your group there like that? Everything that is in the same group has the same representative there. So it just sort of frees us from having to worry about 2 different kinds of things. We deal with not groups, but with representatives for groups. All right, so let's keep going here, right? So I compare F5, and I discover, wait a minute, F5 and F6, those are actually the same movie. So again, I merge F5 and F6 groups, and I pick one of those 2 things to be the representative for the new larger group that is formed here. Now I compare F2, and wait a minute, F2 and F3, those are the same movie, so I merge their groups, and I pick one of them to be the representative for the new group here. So now I have 4 groups. I've discovered that F0 and F1, those are the same movie. I've discovered that F2 and F3, those are the same movie. And I've discovered that F5 and F6 are the same movie. F4 is a different movie here. So I basically only have 4 movies. I just have like some extra copies of some of them. Now suppose that I compare F3 with F0, right? So I discover that F3 is equivalent to F0. So let me back up here, right? Previously we had this. Now we have this. So I took everything that was in this group and everything that was in this group and smooshed them together into one new larger group there like that. So what this saves me, right, is what did I already know? I know that F0 is equivalent to F1, and I knew that F2 is equivalent to F3, and I know now that F3 is equivalent to F0. So I can skip comparing F1 to F2. I don't need to do that comparison because I can tell just by the fact that they are in the same group that they have to be equivalent. So I get to skip sort of like one of my comparisons here based on the fact that those two things are in the same group there like that. So at this point, like this is where I start getting to kind of like skip comparing my sort of expensive things here, because I can just say, oh, they're in the same group. I know that they're equal. I don't need to compare them byte for byte there like that. Right, again, if I compare like F1 and F3 here, I'm like, are those two equivalent? Well, I don't need to compare them byte for byte. I just say, oh, they're in the same group, so they must be equivalent there like that. So it sort of lets me save on my sort of slow file comparisons as the groups become larger. Now, of course, if all my movies ended up being unique, right, and nothing ended up being in sort of like a shared group here, then I wouldn't save anything. But as the groups become bigger, I can kind of eliminate more of those expensive comparisons. So a disjoint set as a data structure, like as a thing that exists in code here, what does it do? What sort of operations does it supply? So we're going to identify our objects by integers between 0 and n minus 1 there. If you want to, like, store other information, you store it outside of the disjoint set. The disjoint set just tracks like numbers, basically. So the operations we can do are, we can ask, what is the rep for an object? So again, an object is just a number between 0 and n minus 1. So if you say, what's the rep for 2? It's like, oh, the rep for 2 is 0. That means 2 is sort of like in the group that belongs to 0 or is owned by 0. All of the objects in a group will have the same representative. So that's how we sort of like determine when two things are in the same group here. We can merge the group containing A with the group containing B. So if A and B are in different groups, we do whatever needs to be done under the hood to smoosh those together into a new group that includes everything in A's group and everything in B's group there like that. The way that we're going to make our merge function is we're going to make it legal to merge two things that are in the same group. It just won't do anything, right? So like we'll return true if you did a merge and two groups were actually merged, like we actually created a new group, and we'll return false if you tried to merge two things that were already in the same group and nothing sort of happened there. And then finally, we can ask, are two things in the same group? But again, this is really just a use of the rep function here, because two things are in the same group by definition if they have the same rep here like that. So the two key operations really are rep and merge here. So we'll look at a couple of ways of building this using some things that we already know how to do, like with vectors and arrays. And then after that, we'll look at a new sort of tree-based implementation here. Okay, so our first version here is going to be based on an array, and you can kind of think of it as sort of like rep-centric here. Like central to this version is the idea of tracking reps. So we know that each object belongs to exactly one group, and we know that each group has exactly one representative. So I can just say for each object, what is your rep here? So the idea is we're going to create an array or a vector, right, of the appropriate size. The array indexes are the object IDs, and the array values are who is your rep here. So I'm literally just saying like, okay, I'm going to have a thing that goes 0, 1, 2, etc. like that. So the value in here is who is the rep for 0. The value in here is who is the rep for 1, and so forth. So this is the rep for 0. This is the rep for 1, and so forth all the way out there. So we're literally just storing for each object who's your rep. So if we sort of take our example from earlier, right, here is what that array would look like. So this 2 here means who's the rep for 0? Rep for 0, right? The rep for 0 is 2. Who's the rep for 1? Also 2. Who's the rep for 2? Itself. Who's the rep for 3? Also 2. So all 3 of those things are in this group with 2 as their rep. Who's the rep for 4? 4 is its own rep. Who's the rep for 5? 5 is its own rep. Who's the rep for 6? 6's rep is 5 there like that. So we're just literally storing for each object ID, right, for each sort of integer that we're tracking here, who is my rep. Oh, hey, look, I already kind of drew this, right? So all the objects in the main group here, they have their rep set to 2. So those are all sort of like pointing at 2 there like that. 4 is its own rep. So it just sort of is like, hey, I'm my own rep because I'm in a group by myself. And then 5 and 6 both have 5 as their rep there, like that. So here's a skeleton of the class that we'll sort of be basing this off of here. And again, like the same group function, that is going to have the exact same definition in all of these versions. It's literally just, is the rep for A equal to the rep for B? So the two ones that we're really going to look at are sort of rep and merge. So this one here, under the hood, we just have a vector of ints. That's kind of like how we're storing the contents of our disjoint set. The constructor just has to like resize that vector to the appropriate size, and then we initialize it so that every object is its own rep. So at the beginning, everything is in its own group here. So we go through the vector, and we're like, who's the rep for 0? 0. Who's the rep for 1? 1. Who's the rep for 2? 2. And just fill out the vector like that. That's what this for loop is doing right here. It's just sort of filling it so that the vector is just 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. Notice, right, like this loop here, that's going to take O of n time, and of course the vector is taking up O of n space to store what we're sort of doing here. That'll be the same for everything, right? Construction will take O of n, and we'll use O of n memory there like that. Like that's not going to change with the different implementations. All right, the rep function. How do I get the rep for an object A? Well, that's easy. That's literally what the array is tracking. So we just return the value in the array at that particular index. So that runs in constant time. That's pretty sweet. That's nice. But how do we merge two things here? Well, we have to loop through the entire array and find all the things that belong to B's group, all the things that have the same rep as B, right? And then change their reps so that they have the same rep as A. So we find the rep for A and the rep for B. If they're already in the same group, right, then I don't need to do anything. If they have the same rep, then like they're in the same group, there's nothing to sort of do here. Otherwise, we loop through everything and we say, are you in the same group as B? Whoops, that should be BR, excuse me. If so, update it to AR there like that, right? This should be BR and that should be sort of AR there like that. This loop here, right, is a loop over the entire array, so that runs in O of n time. It doesn't care like how many things are in the groups. It doesn't care how many groups there are. We always loop over the entire array there like that. So we have an O of 1 for rep and an O of n for merge here. Same group, again, is just based on rep, right? So its runtime is also O of 1 there. So just to sum up, here's this version, right? This version is pretty good at doing rep and same group, but kind of slow at doing merges there like that. And remember, the whole point, right, is we want to save time by doing merges here. So having a slow merge kind of is not super great here like that. Okay, so let's try another version here, right? So we're still going to base this version on an array, but now we're going to orient it around the groups here. So we're going to actually store the contents of each group, like what is in this group, what is in this group here. So we're going to use a vector of vectors to store all the groups here like this. So our constructor has to, of course, create this vector here. And then we want to make all the elements be in a group by themselves here. So we initialize all of the subvectors to be one element vectors here. So if you think of it as something like this, right? It's like, okay, I have sorry, that's a really janky looking rectangle, 0, 1, 2, etc. And then this one here, I create a subvector that just contains 0. And then I create a subvector that just contains 1. Then I create a subvector that just contains 2. So who is in 0's group? It's just 0. Who's in 1's group? Just 1. All the way out there like that. So again, this is just going to take O of n time to kind of initialize the vector and then all the sort of subvectors that we have there like that. But that's the same as what we did before here. Now, finding the rep is a little bit hard here. So we'll say that the rep of a group is just the first element of the vector there, right? So if I have a vector that has 2, 7, and 3, right? That means 2, 7, and 3 are all in a group, and 2 is the rep for that group here. So to find the rep, we first have to find the group that contains it, and then we can grab the first element of that vector. So I have to loop over all my sort of groups, and then I have to loop over the stuff inside of each group. And then if I find a group that contains A, then the index 0 element of that group is what I want there, like that. This bit down here, that should never happen, right? Because every object needs to belong to at least to exactly one group, right? So I will find a group in my inner loop here that A belongs to there, like that. Now, it looks like we have a nested loop here, but actually this runs in O of n time here, because if you sum up the sizes of all the groups, you get exactly n there. So it's not really like a nested n squared loop here. The total runtime is sort of O of n here. So just to note that like this rep is slower than the previous one, right? The previous one was O of 1. This one is O of n. To merge, we have to find the groups that A and B belong to, and then we copy everything from B's group into A's group, and then finally we clear out B's group, resetting it to the empty vector with nothing in it here, like that. So this takes a fair bit of code here. So first we're going to figure out what is the index where A's group is and B's group is here. So that's this sort of step here. Is AI is the index of the group that A belongs to, BI is the index of the group that sort of B belongs to here. So I'm looping over all the groups, and I'm just saying, okay, for each thing E in a group, if A is in this group here, then A's index is I. If B is in this group, then B's index is I there, like that. And again, this looks like a nested loop here, but it's not, right? It's really just an O of n sort of thing here, because again, if you sort of sum up the sizes of all the groups, you get n there. If those two indexes are the same, that means A and B are in the same group, and then we just can't merge them because they're already in the same group there, like that. Otherwise, we loop over everything in B's group. So this is B's group here, like that. And we're going to push back it into A's group. So now everything in B's group is in A, but it's also still in B's group here. So then finally we clear B's group, resetting it to the empty vector there, like that. And then we return true to say that, like, yes, I did something, right? So this isn't quite like relying on rep, but this is like the same code over here as sort of like what rep does there, like that. So again, the runtime of merge, is still like sort of O of n there. And then same group like relies on being just like, is the rep of A equal to the rep of B? So again, that is going to take O of n time, because that's what rep sort of takes there, like that. So if we sum this up, right, this one is worse. The group-centric one is O of n for everything, whereas the rep-centric one is at least O of 1 for a couple of things, right? It's sort of like it's better than that here, right? This group-centric one would be good if we had operations that, like, you know, counted how many things are in a group or returned the contents of a group. We don't have operations to do stuff like that, so it's kind of good at doing things that we don't want to do. But if we had those operations, maybe this one would be like sort of more attractive there. Okay, so now we're going to build something new. We're going to build a sort of forest-based implementation here. We're going to have more than one tree. So if you have more than one tree, it's called a forest here. So the interesting elements to this are, we're not building a binary tree, because each node in our tree can have any number of children, like from 0 on up there. And then another difference from a binary tree here is our nodes don't know who their children are. Like in a binary tree, right, nodes are like, this is my left child, this is my right child. Our nodes here, we only store our parents. We can go up, but not down here. So if you look at a node in one of these trees here, you can be like, all right, who's my parent? And the node can tell you that. It cannot tell you who its children are. The only way to find out like who all the children of a node are would be to loop through all the nodes in existence. So our node structure is going to look like this. Right. So the sort of interesting part of it, the tree structure part of it, is this parent pointer here, like that. That's the thing. It's like, who is above me there? If we're at the root, that will be null pointer to indicate that we're at the sort of top of a tree there, like that. Now alongside it, we have this index here. So we're going to create an array of node pointers. I have a better picture coming up, don't worry, right? So I have an array of these pointers to these sort of nodes here, like that. So the index is where am I in the array. And we need that because a lot of times we're going to make like a round trip. We're going to be like, all right, you give me an index, I take that index and I go into the node pointer, and then I work with the node pointers, and then I end up somewhere and I need to know what index did I end up at. So I need to be able to sort of get back to array land here and figure out what index is a particular node at there. The rank part of it here, that's going to be an approximation of the height of this node in the sort of tree there like that. We'll worry about that later on there. So like for right now, just note that it's initialized to 0, and it's kind of one of the things in our node structures. We are building a forest of node pointers here. So this double pointer here looks a little bit scary, but it's not. Because what we're going to do is we're going to create an array of node pointers, and then each node pointer is going to be a pointer to a particular node there like that. So we're not doing anything with double pointers. This is the only place where you will see 2 stars in this entire data structure is right here. The rest of the time we will just deal with regular old node pointers here. So our constructor is going to initialize total elements to n, just the size of the array there like that. And again, we're not using a vector, so it's not sort of tracking the size of the thing here like that. Then we dynamically allocate our array, and then we dynamically allocate each element of the array as a node there like that. So our constructor, it's still doing like sort of O of n work, but it has to kind of set up this sort of pointer structure here. So once again, I'm going to kind of like go through the example from the beginning here and show what this will look like in this new structure that we're building here. So just to sort of remember, we started with 7 objects. We begin with each object in its own group. We merged 0 and 1. We merged 5 and 6. We merged 2 and 3. And then we merged 3 and 0. And the 3, 0, 1 was the interesting one because that basically took the group from here and merged it with the group from there like that. And we ended up with 3 groups. Okay, so here is what things look like at the beginning. So this here, this is my forest, right? And then my total elements is going to be 7. So each element of the forest is a pointer to a node here. I'm not showing the ranks of the nodes here yet because we're not worrying about that. So in these nodes here, this first value is the index, and then the sort of slashy bit there, that is the parent pointer here. So I'm just not showing the rank part of it here. So every object is the root of its own tree, so all of those parents are currently set to null pointer. Okay, so again, the first thing we're going to do is we're going to merge 0 and 1. So let's see what happens to make that like go. So when we merge 0 and 1, we're going to take 1, which is b, right? And we're going to set its parent to point to 0. So 1 is like, oh, my parent is 0. So 1 becomes part of 0's tree here. So we have a tree where it's like 0 is at the root, and then 1 is underneath it. And then everything else is just in a tree by itself, 2, 3, sort of all the way out there like that. So merge takes, if we do a merge of A and B, right, we find the rep for B, and then we put that underneath the rep for A. We update its parent to point to the rep for A. So the next thing we're going to do here, I think, was 5 and 6. Am I right? Yeah. So again, same thing, right? I find the rep for 6, which is 6 itself, and I make it point to 5, which is 5 itself here. So now I have a tree that is 0 at the root with 1 underneath it. Then I have 2, 3, 4, and then I have a tree with 5 at the root and 6 underneath it there like that. All right, next we're going to merge 2 and 3. Okay. So I do that by setting 3's parent to 2. So now my trees are 0 with 1 as a child, 2 with 3 as a child, 4 as a root by itself, and then 5 with 6 as a child there. Those are my sort of 3 things there like that. And then finally, right, what are we going to do? We're going to merge 3 with 0 here. So let's think about what has to sort of happen here. So we find the rep for 0, which is 0 itself. We find the rep for 3, which is 2. So I'm just saying, like, who's at the top of those trees here, right? So previously I had 0, with 1 underneath it. I had 2, right, with 3 underneath it. Then I had 4, and then I have 5 with 6 underneath it here. So I'm like, all right, who's at the top of 0's tree? It's 0. Who's at the top of 3's tree? It's sort of 2 there like that, right? And then what I'm going to do is I'm going to grab 0 and put it underneath 2 here. So my new tree structure here, let me redraw this here like this, right, is underneath 2, I have 0 and then 1 down there. So 0 becomes a child of 2 there like that. You can see that there's 2 arrows pointing into 2, so that means 2 has 2 children. 2 doesn't know that, right? 2 has no way of knowing how many children it has, but if I go to 3 and I say, hey, who's your parent, it can report 2. If I go to 0 and say, hey, who's your parent, it can report 2 there like that. So now my sort of tree structure, if I sort of draw it over here, right, is 3 is a child of 2. 1 is a child of 0, and 0 is a child of 2. And then over here, 6 is a child of 5. Right? The rep of any group is just the root of its tree. So to find the rep, I just sort of walk up the tree until I hit the root of something there like that. So here's how rep works, right? We grab the ith node, so we do something like, okay, node pointer n equals forest sub I, like that, right? Then we do a loop as long as n's parent is not null pointer. Just do n equals n arrow parent. And then once we hit the top, this is why we need the index. We return the index inside the node there because rep returns an int and not a node pointer there. In the worst case, you could have like a single tall group, right? Like sort of like that, right? So you have the root up here and something down here. If you ask for the rep of the thing at the bottom, the loop has to work all the way up to the top there. So that could take O of n time in the worst case. We're going to improve that. We're going to make it better, don't worry. Or we'll sort of improve it in a second here like that. But that's the basic idea of rep there like that, right? All right, how does merge work? So we find the node at the root of both A's and B's trees here, right? So A is down here. I go up and I'm like, okay, here's M like that. And then B is down here, so I go up and I find N up there like that. Now, those might have like lots of other children, but I don't care, right? I don't care how many things are sort of underneath it there. If M equals N, then we're done, right? They're already in the same group. Otherwise, I'm just going to say N, now you are one of M's children there. So this bit here, this is the interesting bit because that's just a pointer update, right? That's just an O of 1 operation. Right now, up here, finding the reps, those are O of n, but we're going to improve that in a second here like that. So currently, merge has the same runtime as rep. It is just an O of n there like that. Okay, so with this version, everything is just O of n, which is not an improvement over the array version here. We're going to do 2 optimizations that will basically make this constant time. Like, so it'll make rep constant time, which in turn will make merge constant time. So these optimizations, one of them is called path compression, and that's going to work in rep. And the other one is called merge by rank, and that's going to take place in merge here. So path compression is the idea that, like, while we're finding the rep, right, while we're sort of working our way up here like that, we can be taking all the nodes along the path and sort of short-circuiting them so that they all become direct children of the root there like that. So that flattens the tree out along that path there. In merge by rank, the idea is that when I'm merging 2 trees, right, if I have a short tree and a tall tree, I should make the short tree be a child of the tall tree because that keeps the overall height the same. If I do it the other way around, the height increases there like that. So we want to sort of be strategic in how we merge and make shorter trees into children of taller trees there. Okay, so path compression. We already have this O of n loop inside of our reps. So the idea is like, oh, we can add another loop in here. So the sort of improved rep algorithm is, first we're going to do the normal rep stuff here. This stuff here is the sort of normal rep. So we're like, okay, I'm going to find the node n. I'm going to follow it up here to where I find the root. And then I have the sort of root of the thing here. Then I'm going to restart down here with m, and I'm going to work my way up again. But every time I find a node along this path here, I'm going to update its parent so that they all become direct children of the root there here. So I update all the nodes on that path's parent to point to the sort of root up here at the top, right? That the n is up there at the top there like that. That still takes O of n time here, but any future sort of request for any of those nodes along the path, those will now take constant time because they're now one level underneath the root rather than being sort of further on down there. So this is something that improves future calls to rep by flattening out the path as we go along it there like that. Here's a sort of visualization of this here. So here I have a really long path. I have 0 is at the root, and then underneath it, it has 1, and then underneath 1 is 2, and then underneath 2 is 3, and so forth, all the way down here to 6 at the bottom there like that, right? And we ask, who is the rep for 6 here? So we traverse this whole path, we get all the way up here, and we're like, oh, that's the root. But then we restart down here at the bottom, and for all of these things here, we're going to update their parents to point straight up to 0. So I end up with this shape over here, where basically my tree looks like this. 0 is at the root, and it has all the other nodes as direct children. So now if I ask for the rep of any of those nodes here, it takes constant time. So I kind of improve the rep for all the nodes that I sort of touch in one go there like that. Again, it takes me O of n time to do this, but future calls to rep will run in constant time there. Merge by rank is a recognition of the fact that, like, when we're merging two trees, we want to take the shorter tree and put it underneath the taller tree here. So, like, let's say we have a couple of trees here, right? A is height h, and it is taller than B here. So whatever B's height is, it is less than h here. If I put B under A, right, so this is height h over here, and then this height over here is less than h, right? Then A can kind of absorb B, and the total height does not change there like that. On the other hand, if I go over here, again, this is less than h, and then this one over here is a height of h. The total height of this new tree here is actually going to be h plus 1. So the height increases if I put the taller tree underneath the shorter tree. So we want to prefer to put short trees under tall ones there like that. Now, in a binary tree, right, like in an ABL tree, we just store the height in the nodes, and then we can update it when the tree structure changes, because we can just look at our children and be like, okay, the height is the larger of the left or the right, plus 1, forgot that, sorry. And it's easy. But in a disjoint set, I can have any number of children, not just 2, right? And I also don't have any way of figuring out who my children are. I can't look down and be like, all right, which of my children has the biggest height? I have no idea who my children are here. So it's much more difficult in a disjoint set for us to sort of accurately track the heights of our subtrees. And particularly once we sort of add path compression, right? Because path compression changes the heights of things there like that. So instead, we're going to use rank. Rank is kind of like an approximation of height. The relationship between rank and height is that rank plus 1 is greater than or equal to the height, the real height of the sort of tree there like that. It's an approximation, but it's close enough here. When we merge, we find the smaller ranked of A and B, and we make that a child of the larger ranked there. The one exception is when we merge two things of the same rank. In that case, the height has to increase by 1, so you can pick either tree and make it be a parent, and then we just increment its rank here. So only if the rank of A is equal to the rank of B does the rank actually increase there. If we do both those optimizations, we do both path compression and merge by rank, then our runtime turns into something called big O of alpha of n. Alpha of n is a weird function that's called the inverse Ackermann function. The Ackermann function is a function that grows insanely fast here. Like the Ackermann function of like, 2 is like, 200. The Ackermann function of 3 is like, a billion or something like that. So it's like one of the fastest sort of growing functions here like that. The inverse of this grows very, very slowly. Like alpha of n is less than or equal to 5 for any n up to like astronomically huge numbers here. So this is basically a constant, right? This is essentially O of 1 here. So assignment 6 is going to ask you to implement a disjoint set class. I've shown you some bits and pieces of it in this sort of one here, but if you want the sort of full explanation of it there, you can take a look at assignment 6 or the video for it there like that. But other than that, that'll do it for now, everybody. I think, yep, that's it.